So thanks for coming, everyone. It's my pleasure to introduce Subir Sachdev, who will be the Colloquium speaker for today. So introducing Subir is pretty easy, I think, but I'll do the usual spiel of at least telling how important this person is. So, well, Subir, for those who don't know, is kind of an expert on strongly entangled phases of matter. I mean, one of the evidences of this is this book that probably is in a lot of people's sort of office, Quantum Phase Transitions, which, yeah, I mean, basically Subir has driven this whole field. Evidence for that is basically that he has insanely many awards, like he is currently the Virasoro Chair at ICTP, he's the Raman Chair of the Indian Association of Science, he was the Solvay Chair, which is dear to my heart, last year. What should I say? Subir did his PhD with David Nelson, then he moved to Bell Labs. After Bell Labs, he went to Yale. In Yale, he supervised my postdoc supervisor, Anatoly Polkovnikov, and I thought for a while that maybe Anatoly was his first student, but it's not true. Subir told me recently, actually his first student, and this is a very good story for all the students here. You know who is his first student? Ye. You know, Sachdev, Ye, Kitaev. So you can say that even if you are the first student of a new professor, your name can be on a very sort of famous thing, you know? So with that, I will leave it to Subir. Okay. Thanks for coming.
That's a great introduction. Thank you, Reese. It's really one of the best introductions I've received. Thank you very much. And thank you for the invitation to be here. It's been real fun meeting some of you and seeing your beautiful new department here in New York. All right, so as the title says, I'm going to talk about high temperature superconductors and black holes and how quantum entanglement is a common thread that's tied together, recent advances in both fields. I'll leave the black hole part towards the end. My home base is really studying superconductivity, and so I'll tell you a little story based upon that, and also some recent progress based on those ideas and connecting to experiments. And then hopefully there'll be time where similar sort of ideas have surprisingly, and to my good fortune, have played a role in recent advances in understanding black holes. Okay. So let me begin really at the very beginning, the foundation of everything we do in solid-state physics is the Boltzmann-Landau theory of metals. And so let me just recall two extremely important contributions by Boltzmann. One is really just the definition of entropy as a statistical quantity. In particular, Boltzmann showed that if you take the exponential of the entropy, it's related to the density of states. Now, when you're doing classical mechanics, definition of states is a bit complicated. There's an overall normalization that you have to can't quite fix. So that's what Boltzmann called W, the number of possibilities of microscopic configurations. And that's the famous equation that's on his gravestone in Vienna. Anyway, but when you do quantum mechanics, it becomes simpler because you can count states discretely, and that gives you this connection between the thermodynamic entropy and some microscopic quantity, the density of states. And this also then, of course, leads to the absolute definition of temperature. All right, so that's one contribution, important contribution by Boltzmann. The other is the famous Boltzmann equation, where in addition to looking at equilibrium thermodynamic properties, he was asking about the dynamic properties of, say, the molecules in this room. So the key feature of the molecules in this room is that they essentially can be treated classically. Of course, at this time, there was no quantum mechanics. And they collide only rarely. And this was expressed by Boltzmann in terms of some distribution function f sub t of the number of particles momentum p. And at position r. And the left-hand side is a very complicated way of writing down Newton's equations for this distribution function. But his great contribution was the right term, right-hand side, which is the collision integral. It describes the probability for two particles, momentum p and p1, to collide, and the final state, after conserving energy and momentum, has momenta p2 and p3. And the one non-rigorous assumption in this Boltzmann equation was this factor here, which expresses the probability of this two-particle collision in terms of the single particle distribution function. So what this means in effect is this so-called molecular chaos assumption that successive collisions are statistically independent. So the probability that this collision occurs has nothing to do, and the system has no memory of when each of these particles may have collided previously. So that's a very innocuous sounding assumption, but it's the key to the success of Boltzmann's equation. It predicts things like increase of entropy and allows you to compute quantitatively accurately, say, the viscosity of this gas and so on. All right, so, and there's really no argument that he was on the right track, at least for classical gases. So now I want to go to a quantum system, like the electrons in a metal, where I'm going to go from a dilute classical gas to a dense gas, quantum gas of electrons. And amazingly, the same Boltzmann equation applies with just one small change. So if you compare this slide with this slide, the only real change is these 1 minus f factors. And the 1 minus f factors are due to the exclusion principle, telling you that the states you're scattering into better be empty. And it's because of these 1 minus f factors that, again, collisions become rare, not at low density, but at high density. So what happens at high density is that this Fp is either 1, means the states are occupied when you're well below the Fermi energy, or 0 when you're above the Fermi energy. So in either case, this collision term is small. So at low temperatures in any quantum gas, then this term is 0 and collisions are very rare. All the collisions just happen right at the boundary, right at the Fermi energy, in the window of energies of order temperature. So this basic equation is really the starting point of our theory of metals, and it's been extremely successful. Okay, all you need to add are a few bells and whistles, having to do with pairing of electrons to even get superconductivity, and then there's a modified equation in the superconducting state. And really, it's not an exaggeration to say that this Boltzmann-Landau theory is one of the most successful physical theories we have, describing lots and lots of everyday materials, like everything in your iPhone, for example. Okay, so with that success, what else is there left to do? So let me just first describe some of the key features of Boltzmann theory. So one of the things you can compute is the time between collisions. And what you find that the time as temperature goes to 0 diverges. And that's really the key thing. Then the time between collisions becomes long, then the collisions are rare. And it diverges as 1 over temperature squared. And one consequence of this in a metal which has a few impurities is that the resistance grows as temperature squared. And this is one of the predictions that works beautifully in all good metals. Now you can ask, well, suppose I crank up the strength of the interactions. Could it be that if I make U very large, can I make T tau very short? And when is this description going to break down? So when you try to go through that analysis, you find that this is true as long as tau is greater than what we now call the Planckian time, because it's the only thing involved is Planck's constant, h bar, and temperature itself, measured in units of energy. And as long as this tau is much greater than this time, the whole theory should be fine. And so now you see, no matter how large U is, you just make temperature low enough, and this will always be bigger than that. And so end of story, no matter what the metal is, no matter how strong the interactions are, this theory should work. And indeed, it does work. Okay. So effectively, what this means is that the excitations of any metal at low enough temperatures are sort of essentially renormalize your electrons. There are some virtual corrections from particle pairs to change the mass, effective mass, and so on. But the lifetime is very long, and so you don't have to worry about actual collisions in the way Boltzmann taught us we should compute their effects. We can just compute them following the Boltzmann picture in terms of the single particle distribution function. That's all you know. Okay, and I think I forgot to mention, for the quantum system, not only are we neglecting probability, that the probability is independent, we're also neglecting quantum interference effects between collisions. And quantum interference between collisions is what we call entanglement today, essentially. So all kinds of many particle entanglement effects are essentially neglected in Boltzmann's approach, which is the basis of the theory of motion. All right, so now let's, so why am I talking about this? Well, because of course, starting in 1987, when the high temperature superconductor was discovered, we found many, many materials where this doesn't work. And I want to tell you about progress in understanding those materials. So these materials are high temperature superconductors. So superconductivity is a phenomenon discovered way back in 1911 in something just ordinary mercury at some very low temperature. But the materials I'm interested in are these cuprate high temperature superconductors discovered in 1987, 1986, when I was a postdoc at Bell Labs. So that was a very exciting time. Everyone dropped what they were doing and worked on this, including me. I'm still working on it. So I guess I caught the bug early on. Anyway, so these materials can superconduct at temperatures as high as 100 Kelvin. And there's really nothing better since. I mean, that's the sad or maybe happy fact, because there's something really special about these materials. There are these high pressure materials you may have heard about, but those are extremely high pressures that of no practical consequence. This one, in principle, all you have to do is dip it in liquid nitrogen. And when you do that, you can do experiments like this that perhaps you've all seen. In any classroom, that's a piece of IBCO floating above magnets. And while it's superconducting, and it's cool enough, it continues floating. And people have dreamt of many applications, and many are there, but they're relatively small scale. But the dream is that there could be some really long, there'd be a killer app. And if there's one, it's probably this one. So now there are many companies, including this company in Boston called Common Fusion System, that are using materials like YBCO to make the wiring of a big magnet. And then, so the fact that these materials are superconducting allows them to create stronger magnetic fields over a smaller region, and that changes the whole parameter space over which whatever's inside here undergoes fusion. So who knows whether this will work, but it certainly seems like a very worthwhile thing to pursue. Anyway, it gives me enough motivation to continue working on this. All right, so here's an actual phase diagram of, I guess it must be YBCO, as a function of temperature, and the horizontal axis is what's called the hole doping, which is related to this X here of the oxygen. And for our purposes, we're just thinking of density of electrons in a single layer here, and that single layer is a square lattice of copper atoms. So for all the electronic physics, there's a lot of evidence that it's sufficient to just thinking about electrons with various density moving on the square lattice of copper atoms. So nothing could be simpler in terms of models that you could write down. It's the simplest model of interacting electrons with just one band per site, and local repulsion between them, all sitting on the square lattice. But there's the infamous sign problem that's prevented us from solving this as a function of generic density. We only know quite a bit about it in some limiting cases. And so that's really been a huge challenge to understand what the system does. And in fact, the only way we know what it does is from experiments that show us that it goes superconducting at some high temperature. And we're still a long way from computing what this DC is with any accuracy. Now, one of the reasons we're finding it very difficult to compute DC is because the state above DC is where we find something, like we say, strange. So if you took mercury or copper or any of these other things that go superconducting at very low temperatures, the moment you go above TC, like in the blue region here, you would get ordinary mental behavior, where the Boltzmann theory would work just as well. And then you just correct the Boltzmann theory by adding some attraction due to phonons, and that'll give you a pretty good theory of the superconductor critical temperature and many properties. But the trouble here is, I can't even start with Boltzmann theory, because above here, near the highest TC, you don't have a conventional metal. You have what people, it's a terrible name, but they call a strange metal. Maybe a more jazzy name, but anyway, that's what it's called. So what's so strange about it? Well, the most celebrated property is this resistance as a function of temperature. You'll recall that Boltzmann theory goes d squared. It doesn't do anything like that. It's actually a very good linear function of temperature. And this is, of course, the superconducting transition temperature. You can suppress this by applying a field, and the linearity keeps going to lower temperatures. So that was really a property already discovered in a few years, just in the early 90s, in studies of such materials, and it's been studied in much greater detail and really held up to a degree not seen in, well, at least in the conventional materials. There are other superconductors that also show it, but their TCs are quite a bit lower. Okay, but for the purpose of this talk, the thing I want to focus on is not so much the DC resistivity, but what's called the optical conductivity. So the optical conductivity is what you would measure from infrared reflectance or transmission measurements. And from that, you can read off the frequency dependence of the conductivity. And in the Boltzmann theory, you would get an expression sort of like this for the frequency dependent conductivity. In fact, even in the Drude theory, you get this. With the difference that this quantity called m star, which is the effective mass of the electrons, and this tau are independent of frequency. So the only frequency dependence comes from this explicit omega over here. But this is a kind of a very general form that just follows from Drama's Kronig relations. And so you can take the data and fit it to this form and look at what the values of, in particular, what the value of tau omega is. So I'm showing some, actually it's rather old data, but a more careful analysis relatively recently by Antoine Georges and various other theorists and experimentalists. And I just want you to focus on this curve here, which is summarized in this expression. So what they find, first of all, over a range of frequencies smaller than temperature, where this f is about 1, you find that the tau is sort of exactly at the lower bound. It's at the bound at which the Boltzmann theory fails. I said tau had to be bigger than h bar over kT. And furthermore, it doesn't diverge as 1 over temperature squared. It only diverges as 1 over temperature. It's a much smaller tau. So the scattering is extremely frequent. And with such a tau, there's no way you can use the quasi-particle description. Also, then it has this dependence on frequency. And amazingly, the frequency is some function of frequency over temperature. And that's also a very unusual thing. If you put in some light into any materials, and you ask at what frequency does the response change? Well, they would say, well, it'll change according to some energy scale in the system. There could be some energy gap or some Fermi energy or something. There will be some material-dependent parameter that determines the frequency dependence of the response. Here you find it's independent of the material. So you could take YBCO, which is one set of couplings, or you could take LSCO, which is a different set of couplings, and you get the same function f. It only seems to depend upon this temperature. So somehow the natural scale for everything is just temperature, and that's including these kind of dissipative relaxation phenomena. And this is very much against the Boltzmann picture. As you go back to the Boltzmann picture, I didn't emphasize this t squared here, or let's say unit quantum case. That's some interaction strength. That's the probability that they scatter. It surely depends on the Coulomb interactions or whatever there are between the electrons. But here you find it's independent. All right, so those are some of the most dramatic deviations from Boltzmann theory, summarized in this, what's now sometimes called Planckian dynamics, and this is one of the best illustrations of that from experimental observations. All right, so that's where things stood. So clearly, what has to break down is Boltzmann equation. And as I've said, there was one big assumption in Boltzmann equation, which is you could neglect the interference, i.e. the entanglement between the electrons. So really you have to treat entanglement much more seriously if you're going to have a hope of describing the strange matter. So let me just take this through a very simple discussion of entanglement for the graduate students, but maybe you'll enjoy the discussion anyway. So I say here entanglement 1865. Well, of course, that's well before the discovery of quantum mechanics. And that's when a German chemist, Kekulé, proposed a structure of benzene. So benzene has 6 double bonds between carbon atoms, 6 carbon atoms with 3 double bonds. They could be in this configuration or this configuration. And if it was in either configuration, then benzene would not be a perfect hexagon. I don't know how they knew benzene had to be a perfect hexagon at this time, but it seemed natural. So the way Kekulé solved this, apparently by having a dream of snakes eating its own tail, that's definitely in Wikipedia, was that there's resonance between these two configurations. So today we would say that each double bond, this extra bond here, is just a spin singlet of the 2 electrons, up, down, minus, down, up. So this is an entangled state of 2 electrons. And then this resonating state of the two bonds, 2 configurations of the bonds, is an entangled state of 6 electrons. So Kekulé proposed what you'd call an entangled state of 6 electrons to explain the structure of benzene. All right, so why is this entanglement mysterious? Well, that you can date to 1935, this famous paper of EPR, where they said, okay, this entanglement is spooky action at a distance. I wondered if Einstein had ever said that. In fact, he has in this letter to Max Born. This is the German for spooky action at a distance. There he says that he cannot seriously believe in HIT, meaning the quantum theory, because physics would represent a reality in time-space free from spooky action at a distance. So what was he referring to? Well, he's referring to this thought experiment, which today is not a thought experiment, as I'm sure you know. If you take 2 electrons, say, in a hydrogen molecule, with their spins up and down, entangled in this configuration, that's fine, that's happening on the microscopic scale, as Kekulé has taught us. But you imagine doing an experiment where you separate them really far away without disturbing their spin. And then the entanglement is still present. And what this means is that if you measure this electron on the left and you see down, well, the other one at that point will start to point up. It's only after measurement that can be seen some kind of spooky action at a distance. Okay, well, I think today we would say that the resolution of this is that the state of the electrons is not local. It doesn't belong to one or the other, they're just a state. And the electrons were certainly very local in the past when they entangled. And so when you disturb the state, no matter where, you're going to disturb it everywhere. That's my philosophical understanding of Einstein's philosophical objection. Okay, all right, but fine. So we have learned how to entangle 2, and yes, we know today that happens over arbitrary distances, maybe 6, but how about infinity? How do we entangle infinite number of electrons? Is there a theory for entangling infinite number of electrons? Well, that's very much a topic in modern physics today. Lots of people are trying to classify different types of entanglement, things like the fractional quantum Hall state and spin liquids, conformal field theories. Today I'll talk about a much simpler model of entanglement, which we believe is the key to understanding the physical properties of these strange metals, and also black holes, certain types of black holes that I'll get to hopefully if I tell everything correctly. All right, so that's my favorite model, you can imagine, for good reason. And what is it? Well, so after reading about Kekulé's dream, I decided I should have a dream too. And this dream is based on, this kind of illustrates the idea. It's the ancient Indian game of snakes and ladders, which later on for American and British consumption was called chutes and ladders, but it goes back many thousands of years, not thousands, hundreds of years in India. And basically, as Kekule said, entanglement is the snake. And here you have snakes going from anywhere to anywhere. So just start entangling with snakes, all sorts of particles. And that's not a bad description of the SYK model. So here's the model. So imagine you have a bunch of sites which are associated with quantum states, one state on each site. They may not be distribution in space, but that's the way I'm drawing it. There's some labels of some quantum states. And some fraction of them have electrons. And now these electrons are going to tunnel between the states. Of course, if they tunnel one by one, then you'll find that actually it always at low enough temperatures flows to the Boltzmann type description for very similar reasons. So what we're going to say is that we're going to cut off the left-hand side of the Boltzmann equation, and we're only going to allow them to move in pairs. So the entanglement is really at the very top. So that means that, for example, electron on site 11 and site 12 can tunnel together to site 5 and 14. And associated with this cooperative process, there's a complex number. That's, quantum mechanics tells us for every physical process, there's an amplitude, a complex number, and so on. So now you pick any pair of sites that are occupied and then move them to a pair of sites that are empty, and associate with that is a different complex number, which is determined by all kinds of complicated interactions that might be present in your system, and so on. So now you have a series of numbers which is describing the physical situation, and I want you to, the first thing to keep in mind is all of these processes are all happening together, and they're interfering with each other. They're not independent, they're not like sequential. They're all happening and they're all independent. And the hope is that in this model, when you have all these complicated processes, that we cannot neglect the interference. All right, well, find that you can have a hope, and I have to give you these series of numbers and ask you to solve this problem. Well, that's impossible to solve because if you have more than about 30 sites, it's already as best you can do on the very best computers we have today, because the number of states is about 2 to the 30. And you go a little bit beyond that, you simply can't solve it. So what we realized back in '93 was that you can solve it with just one simple assumption. I just assume that all of these U's are independent random numbers. So you don't have to average over anything. Just pick an ensemble of order n to the 4th numbers, but pick them randomly from the same distribution, and then take n large. So we then showed with some assumptions that in fact you could solve the whole problem in the large n limit. Today we know much more about the problem, and this assumption has been thoroughly tested by comparing to numerics at smaller n, and also some analytical work. So I'm just going to go ahead and make that assumption that you can solve this problem just by averaging over these set of random numbers, and the system self-averages. Now this is, given this soft matter work here, this is very different from what would happen in, for example, the Sherrington-Kirkpatrick model of a spin glass. There, you again take a set of random couplings, but the actual state of the system at 0 temperature crucially depends on the set of couplings. That's the spin glass state, so it doesn't self-average at all. Here, because of quantum tunneling and entanglement, in fact it does. So how do you solve it? Well, once you make the self-averaging assumption, it's really quite straightforward. So here's the Hamiltonian. You want to see it in explicit form. These are the fermion operators, and there's these independent n to the 4th independent random numbers. Well, as was being discussed by the students a couple of hours ago, the way you solve it is just one way to solve it. It's just to perturbation theory. And what you find that that you get various graphs, they are order u squared, this one, and this one. I'm sorry, there's some lines that are missing here. In any case, all of these other graphs vanish as n goes to infinity. There's a 1 over n here, whereas this one doesn't. And so the whole thing reduces to these very innocuous looking equations. There's a Green's function for the electron on a site, and it depends on the self-energy. This is just Dyson's equation. And then this you could call the SY equation, and the sigma is the cube of the Green's function. Okay, so when we wrote down this equation in 93, or 92 really, when you're working on this, I thought, well, we'll figure this out. First of all, my first thought was, surely somebody solved this equation. I couldn't find anything. And then I said, okay, well, we'll figure this out in a few weeks. And we did figure out a few things in a few weeks, and then I thought there must be something really wrong here. It's not published, but I did, fortunately, eventually send it in for publication. And the remarkable thing, in fact, these equations have a lot of structure. There's a kind of nonlinear integral differential equations. And we know today that there's features of this equation that really require understanding quantum gravity in some low dimensions to fully understand what's going on here. And I'll try to give you a flavor of that as I proceed. Okay. Anyways, what we could already see then was we had something very interesting. Here was a nearly solvable model, modulo these assumptions we now know to be correct, where you can show by the solution of these equations that there is no particle-like excitations. And then you can then ask, well, how does it respond to some perturbations? Well, this model is, has no spatial structure, but you could try to extend it in some simple way, and then ask, how does current flow? Now, in Boltzmann's approach, the current flows by essentially motion of quasi-particles. They are just single electrons kind of renormalized that are carrying the current. Here, the answer is no. It's really the whole entangled mess that's flowing. Okay, we want to do better than that, but if you want an intuitive description, I really can't do better than that. We can compute things about this current flow, and that's what I'm going to describe in the remaining part of my talk. And so what is, okay. Anyway, so what were the things we could compute? So one of the things we could compute for certain quantities, not the transport, because there's no transport in the simple model, but it has exactly this property that we were seeing was already apparent in the experiments in those days, that the scattering time is given by this kind of function. That is just h bar over kt times a function of frequency divided by temperature. And the strength of the interaction, meaning u, doesn't appear anywhere. It's just a universal function of just temperature and Planck's constant. Gives you the full scaling behavior. So this kind of entangled spoof of electrons has exactly the Planckian behavior that you see in experiments. Okay, and that certainly got us very excited. I should say this behavior, although we intuitively expected it to be there, it wasn't until this very nice paper by Antoine Georges and Olivier Parcollet that it was mathematically established. Another property that appeared in what I call the GPS paper, again with the same collaborators, is it has a rather strange looking entropy. So there's a third law of thermodynamics that says the entropy must vanish at zero temperature. Okay, but there are some models that violate that. For example, there's something called the Pauling's ice model. It's some very special model of frustrated interaction which has an exponentially degenerate ground state. So that's a very special model, fine-tuned to give you an exponential degeneracy of the ground state. Exponential is the system size. If you just perturb it at all, it would disappear and obey the third law of thermodynamics. So here we found that if you take this very specific order of limits, first take the thermodynamic limit and then the zero temperature limit, then you found a non-zero value. So there seemed to be a non-zero entropy, zero temperature entropy density. I want to distinguish this from a ground state degeneracy, which would be the ground state entropy, meaning there's an exponentially large degeneracy of the ground state. And there's absolutely no reason with this model or any other model, and the way we have derived it, to have any ground state degeneracy. So it's really was the first model that had this feature, which is zero temperature entropy without exponential ground state degeneracy. Today we know that the D of E is this e to the ns, not the density of states that Boltzmann used, times the smooth function of energy. So this is what the actual DOV looks like from a numerical diagonalization. And the reason this entropy appears is because these levels are very close to each other. They're not degenerate, but they're exponentially close to each other, down to the lowest energy. And that's really the feature that leads to the absence of quasi-particles, and the presence of these very low energy states also leads to this kind of Planckian behavior. Anyway, that also, but from our point of view in 2001, this was a curious feature which kind of dampened our enthusiasm because no experiment on the high temperature superconductors or the strange metal had ever shown anything like this. This was great, so this is, oh yeah, we should really keep working on this. But this said, well, okay, this is curious. Something is bizarre about this model. Yes?
In the quasi-particle picture, tau of omega has very clear intuitive meaning. What is the meaning of tau of omega in this picture?
Yeah.
How to think intuitively about it?
Well, you take some response function with respect to some external perturbation at a frequency omega, and then you look at how, after perturbing a frequency omega, how the system relaxes to its thermal equilibrium state, and that will give you some measure of how.
But there is no more mechanistic way to think.
No, I think basically you just look for any natural time scale of equilibration. So the system, we know from numerics, and also it thermalizes. It's sort of the best, it's the fastest possible thermalizer, which makes it the worst possible quantum computer. It goes to thermal equilibrium as quick as anything can. But yeah, so you come up with some definition. And depending on your definition, this function f will be different. But in all cases, we believe it will be universal. And only depend on your definition and nothing else.
Do we more or less know the dependence of S naught with Q? Like
Yes, we do. There's a formula. There's an exact formula that's in the GPS paper. I only give the value at Q equals 1/2.
Does it happen that Q equals 0 or 1, you get S naught 0? Or
Oh yes, absolutely.
Okay.
Yeah, then that's a
Okay.
trivial system. There's only a, it's fully filled up, fully empty. So it's maximum at Q equals 1/2. There's a plot of that function in this paper. So in fact, when Kitev looked at the simplified model that I'm describing today, I'm not actually describing the model we solved then, which is a bit more complicated. He was writing down the solution on the board, and he wrote down, he did it a very different way, and he got some entropy. He wrote an expression. I was watching on Zoom, and I took that expression and compared it to our expression and was not agreeing. I said, oh my God, we made a mistake. and so I emailed him. Oh, he said, no, there's a typo in the board. When he sent me the right expression, everything was good. Anyway, that was a very happy moment for me that we got it right 20 years ago. Even the numbers are completely right. All right. So this, as I said, this behavior made us happy. This behavior made us not so happy, and that's probably the reason, we just stopped working on this for a while. Then Kitev came on the scene, simplified things, and a lot of very smart string theorists started working on it. And then, even condensed matter theorists got into the game, and progress was made. So, of course, what motivated the string theories was the connection to black holes, which I will talk about in the last part of my talk. And at what time, please? At 5:30, right? 5. Oh, well, okay. No, that's 5.
Good try.
Anyway, so if I don't get to the end, it turns out, I didn't know about anything about black holes in 2001. That certain types of black holes have both of these properties, quite amazingly. So this SYK model turned out to be just the ticket for describing black holes. And it's not just the ticket for describing strange metals yet. Anyway, so let me continue with strange metals before I go to black holes. So we have to perform this model. So the model is a zero-dimensional model. And to any condensed matter theory, there's no way you can describe something as complicated as two-dimensional strange metal by a zero-dimensional model. You need to make it two-dimensional. And there's been a huge effort in the last 10 years or so to do just that. And I just want to tell you about one particular generalization to 2D, which we think is the right way to proceed, which actually does agree with a lot of experimental observations. And this is work with my former student, Avishkar, who's now at Flatiron, former student, Hayugo, and former postdoc, Ilya Estes. So let's go back to now real physics rather than toy models. So we want to describe this phase diagram of the cuprates, in particular the metals. I've already told you that there's what's called an ordinary metal here, a strange metal here. In the pink region, and there's a lot of complicated physics, people call it the pseudo-gap metal. For this discussion, all I want to say is, let's look at the Fermi surface, that is the boundary in momentum space between the occupied states and the empty states. That's something that makes sense even for a strange metal, actually. So if you look on the ordinary metal, you get exactly the Fermi surface. You will see this is a photo emission experiment, which is like the photoelectric effect. Allows you to read off the boundary. And this is exactly what you expect in the Boltzmann-Landau from the liquid theory. On the other hand, in the pseudo-gap metal, you have a very complicated looking mess that doesn't agree with anybody's theory, any simple theory. We have our own favorite theory of it, having to do with spin-liquid correlations, but I don't want to go into that.
Sorry, what's being pictured?
This is as a function of momentum, kx and ky. This is a photo emission experiment, and they've done some analysis to highlight precisely the regions where you have electrons right at the Fermi energy, the boundary between the occupied and the unoccupied state. So momentum space, that's what we call the Fermi surface. And there's certain theorems about that Fermi surface in Landau Fermi liquid theory. So on this side, those theorems are obeyed. Here, there aren't. Anyway, so the point of view we've taken, and many others have taken, is this is the most fundamental phenomenon. You have some kind of quantum phase transition between one metal and the other metal. And that's the central actor of everything. So when you're near this quantum phase transition with these two different types of metals, you get the strange metal and the high TC superconductor. So to make our life simple, let's just remove the superconductivity. I don't know how, but theoretically we can just banish it, even though it's the most interesting thing there. And just try to work out a theory which involves a change in the Fermi surface of these electrons. So this is something that, again, you can read my book, and there's many other books. A lot of work has been done, and of how you can have a quantum phase transition between two different metals with different shaped Fermi surfaces. I don't want to go into any details, especially since I have to end by 5. But in all of these theories, there's one essential thing that appears, that you have to introduce some kind of scalar field. It could be a Higgs field, it could be a broken symmetry autoparameter, and the scalar field becomes critical right where you have this change in Fermi surface. So there's been an enormous amount of work on exactly how this quantum phase transition proceeds. Again, I won't say anything about it, but to jump to the final answer. So what we have to do is to take this theory of the Fermi surface and then take this scalar field and couple them together. So if I just look at this term here, this is very much like the Yukawa coupling of quarks, nucleons coupling to a boson. The meson, this is the original origin of Yukawa's coupling. It's also the coupling with the Higgs coupling between the Higgs field and the fermion. That's a little closer in spirit to what happens here. And then there's a coupling which is just a number. So to make this problem solvable, we do two things. We give some extra labels which are fictitious, but more importantly, we make we add a term which is spatially dependent. And what does this mean? So the spatially dependent thing is that, remember I had this critical coupling where you went from one Fermi surface to the other. It means that this value of SC is not the same everywhere in the sample. So one value here, another value there, another value there. And that's the most important thing you have to include. So we learned how to do all of that in some systematic way using what we learned about systems with random couplings in the SYK model. And when the dust settles, you get exactly what you wanted. So this is work that published recently, well, about to come out of PRL, so relatively recent. So this is, for example, the calculation of the resistivity as a function of temperature, and also doping here. And right at the critical doping, you have a linear function of temperature. But we can do more. We can actually compute the optical conductivity. This is the actual experimental data for the real and imaginary part of the conductivity, I think. And this is what we get. It's essentially the same shape. And most interestingly, there was this tau of omega I told you about. This is the experimental observation I already showed you. And that's the kind of theoretical results we get. And finally, the problem I told you with the SYK model, the zero temperature entropy, disappears, and we get actually this log correction entropy, T log T, which is actually observed. That is also what's seen in many experiments. Anyway, all right, so I have 10 minutes, just over 10 minutes to teach you about black holes. Okay, some of you know much more than me. Okay, so as I've emphasized, it really had to go beyond this toy model to solve the problem, we hope, to make progress on the problem. I think we've done that for sure, of the strange matter. But it turns out, quite amazingly, for reasons I will now quickly describe, in certain black holes, so we don't have to go beyond this toy model. It is exactly what's needed. And these are so-called extremal or near extremal black holes. And these near extremal black holes are obtained by taking a charged black hole with a net charge Q, which almost certainly there's none out there, or a rotating black hole, but which is rotating at a very high velocity. And maybe there's some out there like that. So for these black holes, you can say something more about the low energy density of states. So let me just summarize how that works. So black holes, as you all know, are solutions of Einstein's equations, first found by Schwarzschild, where matter is so dense that light cannot escape them. So this is very dense matter, but in fact it's even denser than that, because Einstein's equations say that the matter collapses right to the center of the black hole. So there's some singularity, which is why nobody really took these solutions very seriously. And anyway, any serious attempt to treat the singularity requires a quantum description. And really the first person to start thinking about quantum mechanics of black holes, first persons, I should say Bekenstein and Hawking, and maybe John Wheeler before them, I guess. And one way to phrase the argument, they never used the word entanglement, but we can now use it, very useful word. You go back to this famous EPR experiment and imagine doing it where one partner of the EPR pair falls into the black hole and the other stays outside. Well, since there's nothing really special going on at the horizon, you don't even know whether you're going through the horizon as you're falling into the black hole. You certainly will know when you hit the center, but before that, you don't, at least. Most physicists believe there's nothing there. So then these entangled pairs are still entangled. So this means if I'm safely outside the black hole and I have this half of the qubit with me, since I can never access any conceivable experiment, the qubit that's inside, this is effectively a random qubit. And Boltzmann taught us randomness is entropy. So, and entropy also is related to temperature. Of course, I'm paraphrasing, but anyway, that's the quickest argument I know, that to an outside observer, it will appear as if the black hole is almost like a black body with a certain temperature and entropy. So Hawking, in fact, gave the precise expression for this entropy. is this expression here. This factor of 4 is due to Hawking. And involves fundamental constants of nature, like Newton's constant in the velocity of light, and h bar. It's really the first formula that involved g and h bar together. But what's most peculiar is this fact that it's proportional to the area of the horizon. And this is very different from any system that we met before, where the entropy is proportional to the volume. And if you take this point of view of this entropy as being what we can all call an entanglement entropy, you can sort of understand that, because the number of entangled pairs is, and all the entanglement has to happen at the surface, and if these entangled pairs at the boundary, the density of these is proportional to the area. Okay. All right. So that's Hawking's famous formula, and now I can talk about the two fundamental results which are now inscribed on two gravestones. This is Hawking's gravestone in Westminster Abbey. He actually wrote the Hawking temperature, but anyway, so I added the So these are the battle of the gravestones. Is this consistent with this? So if there's an entropy, then Boltzmann told us there must be a D. What is the D? What is the quantum system whose D gives you the Frankenstein-Hawking entropy? So that's been a fundamental question that's been deriving a lot of research, starting with the Hawking's amazing paper in quantum gravity and string theory. And there have been some answers, but using supersymmetry. But we want to go beyond supersymmetry, because any black hole at low energy doesn't have supersymmetry, even though at high energy they may be. Okay, so now for charged black holes, so why am I focusing on so-called extremal black holes? Well, amazingly, if you just take the Hawking formula for a charged black hole, you find that it has this famous zero temperature in it. That as temperature goes to zero, the entropy is finite. I was totally unaware of this, certainly in '92. I only learned this in some 2008 or something like that. But when I heard this in 2008, suddenly I remembered, oh yes, there's a model which has exactly this property. So it's, there weren't any other quantum model that had such a property, except for some fine tuning leading to exponentially large degeneracy. All right, so that immediately suggests there's some connection to the SYK model, as I kind of realized in I'll show the reference in a minute. There's another feature where black holes also have what's called a ring down time. If two black holes merge, then there's a ring down time before they become a perfect sphere. Now that's a purely classical behavior. You can compute the ring down time using GR. However, if you express this ring down time, tau, in the Hawking temperature, it has exactly this form. So this is also something I learned around 2007 or so. So here's another striking similarity between strange metals, SYK model, and black holes. All right, so now through the work of Patel and others, we can really make the correspondence very precise. So let me just summarize the connection that I noted in 2010, that both SYK models and black holes have this common relaxational time of h bar over kt. And I even said in my book, actually, this is a kind of a lower bound to any relaxation, so it's the maximal time to chaos. That would be the modern way of talking about it. And then they have finite entropy in the zero temperature limit. Now, if I believe this has something to do with the SYK model, then this would immediately imply that this entropy, the zero temperature entropy of charged black holes, is not realized by an exponentially large ground state degeneracies, as is the case in calculations we have, starting with Stromer and Wolfa, of any string theory realization. Where because of supersymmetry, you just have an exponentially large number of ground states. All right, so what is the answer for the density of states then? And now that's the calculation that's been done, and very quickly I'll summarize that. Oh, I have 4 minutes. No problem. So what would you want to do? Well, you take to compute what Boltzmann says you need to compute to show there's an entropy. You would say, well, you take your action for Einstein gravity. Since there's a charge, you also need to add in the electromagnetic field. And you look at saddle points of these actions. And there certainly are saddle points of this action which describe a charged black hole. And then Feynman tells us what we have to do to compute the partition function and the density of states, which is the inverse Laplace transform of this. Well, you just do a path integral of all possible configurations about the saddle point of both the metric and the gauge field. Totally impossible. It's not even clear this is well defined, certainly in 3 space and 1 time dimension. However, and also before, I should also mention the following. If you take this saddle point, which is shown here, this is an ordinary space. It has an angular direction and a radial direction I call zeta. And you write it in imaginary time. And in imaginary time, when you're outside the black hole, the metric looks like this. It looks like a cigar. The time is periodic in imaginary time with period h bar over t, as perhaps most of you know. And space itself, this time basically ends at the horizon. So basically you have to do the path integral over this cigar. Now, that is exactly what Gibbons and Hawking boldly set out to do. And they said, well, we'll just do the path integral, and we'll just do the saddle point and just see what you get. Forget about the fact that the fluctuations are totally well not defined. And that's how you, in fact, reproduce as one way of getting the famous Wittgenstein-Hawking entropy. So what we know today is that you can even go beyond just the saddle point. And the remarkable thing is that the fluctuations, the leading fluctuations about the saddle point, are given by a theory in 1 space and 1 time dimension. And what's happening here, is on this picture, which I really should reproduce on that slide, is that, remember there's the radial direction and the angular direction. So the low energy physics turns out to be dominated completely by the radial direction. The angular modes, you can just take the lowest angular momentum harmonic. And so you just get a theory which is exactly in the 2 dimensions shown here, in 1 space and 1 time. You just have to do the path integral on this cigar. And that theory is what's called the JT gravity theory, projective tidal bound. All right, but now life is much simpler, it's 1 plus 1. And then amazingly, since gravity is mostly gauge degrees of freedom, you can exactly simplify this theory to a theory of the boundary, where you only have time. So basically, you only need to worry about a theory on the boundary here at some distance from the horizon, which depends on exactly when this 2-dimensional approximation breaks down. And the remarkable thing is that this action that you get here is exactly the action you would get from the SYK model. That is, you can do 2 different calculations. You can start with the SYK model I just showed you, and then go beyond the simple graph counting I showed. That's what Kitay showed how to do, and write down some low energy action. Or you can start from the Einstein-Maxwell equation in the background of a charged black hole, which is what Gibbons and Hawking set out to do, and make some dimensional reduction that was pointed out by Mandelsena, Steinberg, and Yang. You get the same action. And then furthermore, Witten and Stanford showed how to evaluate this exactly. All right, so beautifully in the end, you get the answer for the density. You answer Boltzmann's question. What is the density of states? Well, there is this e to the entropy factor that that's the, that comes from the naive application of Boltzmann's rule. But now this doesn't tell you anything about the energy dependence. And the answer for the energy dependence is the Sinch function of energy, where again, it just only involves the same parameters that appear over here, fundamental constants and the area of the horizon. And this Sinch is exactly the same for the SYK model or any extremal black hole. It's this function here, which we now know, thanks to this path integral over quantum gravity. It applies also to any black hole. It's a kind of a universal feature. This particular prefactor, which is independent of energy, but it depends on the area. Was computed recently by Eliassi, Murthy, and Turiachi. And this, the only thing that depends on this number. That requires some information on the matter content of the universe. That's the only thing where the matter content, what's actually inside the black hole matters. Everything else is kind of universal.
347 over 90.
Yes. But the cinch, which is the most important factor.
Like, is that the value in the supersymmetric center model or something like that?
No. So that's no supersymmetry here. It's counting the number of massless
like
particles. You're just knowing there's a graviton, there's a photon, maybe a massless neutrino. That's all you need to know.
As you could count the neutrinos.
Something like that. I don't know whether they put the neutrino here or not. You just have to take massless particle. That's all. Yes. Now, if you know, of course, there are corrections to all of this, but the correction will be higher powers of energy here, and basically inverse powers of the area. All of that will depend on details of the theory. But there's anyway, so this, yeah, okay. So that's what we've learned from the SYK model. After this long road, we have understood this stage. All right, so this is a bit tongue-in-cheek way of describing it. I'm not saying that actually an SYK model inside a black hole, but you're looking at it from the outside. For charged black holes or extreme rotating black holes, it's a pretty good quantum simulation. It's the first thing you will measure if you are ever able to measure a quantum correction to GR. All right, so to conclude, the SYK model's claim to fame is it's really one of the first solvable models to describe extreme quantum entanglement, which led to the loss of identity of the particles. Now, this is very different from things like the fractional quantum Hall effect, where there's also lots of entanglement, but there are fractionalized quasi-particles. Here, there's nothing like that. And some extensions of this, we believe, are starting to give us a description of the strange metal in cuprates and other coordinated electron materials. And there's a dual description in terms of these boundary gravitational modes, where it actually has led to the computation after many years of the low energy density of states of charged black holes. Thank you. Sure.
One question.
Sorry for going 4 minutes over.
The common features are in between the low energy effective action for SYK
Yes.
and the spectrum of near extreme black holes.
Yes, that's
How
why there's
much-
a direct connection.
How much of SYK is needed? Because you're only using a small part of the internal.
Sure,
You're
yeah.
using the universal. feature.
Well, basically, what you need is any kind of interacting quantum model which has in 0 dimensions, which has an emergent SL2R symmetry. I think, as far as I know, anything we've studied, as long as you have that emergent SL2R symmetry in some many-body system, you will get all the other properties. You will get the zero-temperature entropy, and an SL2R is again the fundamental reason these, the surprising thing that this gravitational theory gives you the same action, and that's because this ADS2 also has an SL2R symmetry. So ultimately, this SL2R is the key to everything.
And just as a follow-up, can the presence of this SL2R rule out some simple models, for instance, with local interactions?
Well, I know there's certainly many, you could take them. Well, first of all, I should emphasize in the SYK model, you don't actually need to take an average, it's self-averaging. So you just take some set of U alpha, beta, gamma, delta, which are kind of generic. I mean, if you took a very special pattern, all of them equal, there are just 2 types, then you'll get some other physics, probably there'll be a gap and so on, also broken symmetry or something like that. But you can take any kind, basically you need to avoid the trivial states. As long as you avoid the trivial states, it seems this is what you get. I mean, there's no proofs of any of these claims, but that's our experience.
Are there more questions?
Just a simple question. So the key feature of these materials is they superconduct.
Yes.
So I guess, so how does now that you have a really nice understanding of the normal state, does
Yeah.
that help?
Well, we hope so. That is my program for the next 10 years. But this paper here, well, where did it go? I'll at least just say this, we're starting to look at that, and this paper that I mentioned where I talked about the strange metal properties, we started, where did it go? Yeah, this paper, if you look at the title of the paper, Superconductors. So there is, in fact, this model is unstable to superconductivity. I won't say we can understand TC from this simple model. They probably need to worry. It's just too simple for that. But there are certain features of the superconductivity of how the superfluid density depends on energy temperature, for example, which we discuss in this paper. It seems to
Oh, you get pairs.
yeah. So that is this basically. So what this model does for you, this interaction, this Yukawa interaction, having the non-random, spatially non-random and spatially random term, can do two things. One, it can scatter the electrons so strongly that the electrons don't exist. But it can also pair whatever this mess of entangled electrons is and have a form of Cooper pair. So it has both effects, and we can write down the equations to solve for all of that. But it's at a rather mean field level, and I don't think that's very accurate. But that's definitely what we are starting to work on.
Thank you.
More questions, personally?
Can I make one? So this is actually a comment and a question. So if I consider the classical cousin of the SYK model, which is the p-spin model, and I solve for the dynamics below TT, so in the aging regime, the non-equilibrium dynamics for the correlation and the response, I also find this conformal invariance. And that is easy to understand what it is. Basically, there are kinetic constraints that reparameterize the flow of time. In your case, you have the same conformal invariance, but at equilibrium.
Okay, so let me, I can answer that before you get to the next question.
Yeah, no, okay.
So these classic equations of Cugliandolo and
Kurchan. Yeah.
They have a time representation symmetry.
Yes.
However, they have a broken time translational symmetry.
Yes.
So that makes it very different. These equations for SYK model do not break time translation invariance, but they have the conformal invariance, time representation invariance. So I think they're very.
No, I'm not claiming that they're equal.
Yeah, but I think that
I
makes
just want to know what is the physical
entirely
reason that causes this reparametrization invariance. In the glassy phase is because the system is aging. So the kinetic constraints that reparameterize the flow of time. In your case, you don't have glass and you are at equilibrium. So what is the physics of this reparameterization?
Entanglement. What else can I say? But formally it's similar. The reason you get if you go back to this.
But the system is classical at an infinity. I mean, it's not.
No, it's not classical. It's highly quantum. It's not classical at all. This is a quantum entanglement.
Well, but you take a saddle point.
You
take the saddle point. This equation are at the saddle point.
It's h bar is non-zero even at the saddle point. There's an n. It's not an h bar saddle point.
Okay.
So what happens is that this omega is not important in the low frequency limit. That's very similar to what you said happens for the p-spin model with classical spin class.
Yeah, if you
So that gives you,
derivative.
once you drop that omega, there is a very natural time representation invariance. But the ground state, in addition to the time representation invariance, the ground state solution, which gives you this length in time, to get this, you also need the ground state to be time translation invariance and have SL2R's exact symmetry. You do not have that in this glass problem. So there's a second ingredient which is entirely missing, which is crucial to everything I've talked about.
So when we say that the conformal invariance is a direct consequence of the entanglement.
I mean,
Well,
I would say turn around, define it.
Well, in the classical case, is a consequence of aging.
Because this is leading to some next.
No, there is no conformal invariance in aging. Not conformal. There's time representation invariance. It's different from conformal invariance. There is time representation invariance. Conformal invariance requires time translational symmetry.
Okay.
The rest is
Then
40 years, I think. So let's thank Subir again.